Okay, welcome to the Math 1030 or 1035 Exam 4 review. This exam was created in summer 2023. So, let's get that off of there. There we go. Module 7, Set Theory and Logic. So here we have problem number 1. Let U be the universal set. So U consists of the numbers 1, looks like there's nothing missing, all the way up to 16. So that consists of all the numbers for this problem. A, B, and C are subsets of U, and so you'll notice that everything in A, B, or C are also somewhere in the set U. Therefore, A, B, and C are all subsets. List the elements in the set A intersect C. So you want to be able to look at A intersect C and think in terms of in both A and C. So the intersect symbol is very similar to the capital A symbol. It's helpful for remembering that symbol is for and. Okay, A and C. So we're taking a look at A and C and seeing if we can spot numbers that are in A and C. And there we have them. 4 and 15. So the answer for part A is A intersect C would be the set of 4. What happened with my, there we go, and 15. Now it does say list the elements. I don't know why that, everything moved, whatever. Since it says just list the elements, I would give full credit for just 4 and 15 in the list. However, if they say find the set, then you want to include the set brackets, as I have these curly brackets around the 4 and 15. Okay, next up we have the A complement or B. So in English this would be outside of A or in B. So anything outside of A or anything in B. Now or could be in one or the other or both. So I would probably start with the fact that they can be in B. I know the answer will consist of at least everything in B. Now it also says also anything outside of A. Now the concept of outside, you need to know the universal set so you know what everything is, because outside of A only means everything in the universal set that's not in A. So if we go into A, into the universal set, and we cross out everything in A, etc. Let me actually do that. I'll erase this in a minute. 3, 4, 6, 7, and 15. Now looking at that list, that's everything else in the universal set that's outside of A. So 1, 2, 5, 8, 9, 10, 11, 12, 13, 14, 16. All of these numbers are outside of A. Now some of those numbers are probably already in the list that we have that are in B, but anything else we should include. So 1 is in there, 2 is not. Let's include 2. 5 is not. 8, 9, 10, 8, 9, 10, 11, 12, 13, 14. That now includes everything that's either outside of A or in B. And some of these numbers are in both outside of A and in B. That's okay. The concept union is or, and you can say in one or the other or both. So the stuff in black are in B, the stuff in blue are in not A or outside of A, and then the stuff in red, there were a few. Let's see, what were they? 12 and 13 and 16. Those numbers were in both outside of A and in B. So, but you don't list them twice. You just list them once. So this is the list of all the numbers that are outside of A or in B or both. Okay. Last, part C, list the elements in the set. Okay, so we want to think both of these symbols are AND. So maybe we work on B and A first. And then we can work out outside of C. And this will give us a list of numbers that we can then look for what's in both of those lists. So B and A. So looking at B and A, what's in B and A? 7. Looks like that's it. 7 is the only number that's in both B and A. Not much going there. Now, what's outside of C? So if we again go through the universal set, comparing with C, if you see it in C, cross it out from the universal set. There's a bunch of stuff in outside of C. In fact, it's so much that maybe we just look at this list right here as outside of C. And then just compare what is in both the set of 7 and outside of C. Well, is 7, there it is, 7 is there, and 7 is there. 7 is in both outside of C set and in both A and B sets. So, B and A and outside of C consists of the number 7. So 7 is both in A and B, and it's outside of C. So this question is mostly about understanding union and intersection and complement. Hopefully that makes sense. All right, next up, number 2. A survey asked 150 people, what beverage do you drink in the morning? 76 people said they drink tea. 85 people said they drink coffee. 45 people said they drink tea and coffee. Now we actually go about filling out the Euler diagram, the Venn circle diagram, with reverse order. So this will be the first thing that we do. 45 people said they drink tea and coffee. So let's let this first circle represent tea drinkers. The second circle, coffee drinkers. And we are given that 45 people said they drink tea and coffee. So there's 45 people in the overlap between the tea and coffee circles. So that's the first thing. The next thing, they say 85 people said they drink coffee. Well, we already have, of the 85 people, 45 that are in the coffee circle. 85 minus 45 is 40. That means that there's 40 other people in the coffee circle to be represented. What we have now is 45 plus 40 is 85. There's a total of 85 people drinking coffee. 45 of them also drink tea. 40 of them just drink coffee. Okay, next up, the third one. 76 people said they drink tea. Well, of the 76 people in the tea circle, 45 of them are already listed. So that leaves 31 people that are in the tea circle. So we now have 31 plus 45, that's 76 people in the tea circle. Finally, we get to that there are 150 people total. So that's 150 people in this entire universal set that's in the rectangle. 150 people. But we already have 3 sets of numbers in this rectangle. So if we subtract those, And this is where I would trust technology over my brain. So let me just make sure I get this right. Now, although I'm using a graphing calculator for demonstration, the keys are very similarly laid out to the common TI scientific calculators, and you should be able to follow along. You only get a scientific calculator for the exams, but this should not interfere with your ability to follow along. Okay, 34. So there are 34 people total. There are 150 people total in the universal set, and 34 of them aren't on here yet. They go right here, or you could put them here, or here, or here, or anywhere outside, but I typically use this bottom right corner. So now, if we were to add 31 and 45 and 40 and 34, we would get 150 people total. Now that we've filled out the Venn diagram, we can answer the questions, like how many people drink only tea? Well, only tea would be these 31 people. How many people drank tea or coffee? Well, now the concept again, or, is one or the other, or both. So there are some people that drink only tea, only coffee, and some that drink tea and coffee. They're all three in the set people that drink tea or coffee. So this would be the 31 plus the 45 plus the 40. That would be 116, I believe. And then finally we have how many people drank neither tea nor coffee. Those are these 34 people that I don't know what they were drinking in the morning. Hopefully it's water and not something stronger, but there's 34 people that drank neither tea nor coffee. Orange juice, yeah, that's what it is. I don't know what they're drinking, but it's neither tea nor coffee. I hope this makes sense. All right, we get to question number 3. Complete each column of the truth table below. Now the truth table, there really are 3 basic concepts in the truth table that we need to look at, and these are all 3 of them in this question. These 3 symbols. The way I like to do these truth tables is to know what, based on the symbol, what the assumption is, and then when do you change that assumption. So what I mean by that is this symbol is AND, or the intersection. This symbol is implies. So like if, then statements. And this symbol is or the union. So I don't know what Q and S stand for in this problem, but they're both whether something's true or false. With the AND symbol, you assume false. Because in order for everything to be in the AND, everything has to line up. So essentially, is Q true and S true? Yes. Is Q true and S true? No. Is Q true and S true? No. Is Q true and S true? No. So most of the time when you're doing the AND intersection, the answer is false, because everything has to be true in order for you to say, yes, they're both true. So you assume it's false. So what I will typically do is I will just start with everything being false, and then know when you change that assumption. A true and true equals true. That's the exception to assume it's false. So here we have a true and true. So that's the one that doesn't follow the assumption. What I like about doing it this way is I can fill out almost all of them correctly right off the bat and only look for one case to change instead of think about every single one individually. The or is next easiest. So or is Q true or S true? Is Q true or S true? Or includes both, so definitely yes. Is Q true or S true? Yes, Q is true. Is Q true or S true? Yes, S is true. Finally, we get, is Q true or S true? No, they're both false, so that one is false. So they're almost all true. So this one, I assume true. So I would start off with, well, let's just assume they're all true, and I just got 75% of this problem right, or this column. But then know when the exception is. The exception is a false, and a false equals a false. Here we have a false and a false. That's the one we change to false. We'll get more practice on this on question number 4. This really nice way to go about this. Okay, and finally the implies is probably the hardest one, but I like to think in terms of cloudy and rainy. So I would think Q is rainy and S is cloudy, because rain implies clouds. That's a true statement. If it's rainy, there are clouds. That's just, you can't argue with that in any valid way. So think of this as rainy, and this is cloudy. And then we ask ourselves, if it's rainy, is it cloudy? That's a true statement. Rainy implies cloudy. If it's rainy, it's not cloudy. That makes no sense. So this one, it's raining and there are no clouds. That's false. That makes no sense. It's not raining. There are clouds. That's definitely a possible situation. That you see that. It's not raining and there are clouds. So that is fine. And finally, it's not raining and there are no clouds. Wow, beautiful day. The only one that doesn't make sense is it's raining and there are no clouds. That's just not logical. That situation would prove false the claim that rainy implies cloudy. So if we're trying to say that rainy implies cloudy and we find it's raining and no clouds in the sky, then that would disprove this implication. So this one, it's easiest to assume true and then know that a true and false equals a false. So all of the cloud, rainy, everything, if you just go with the assumption that this is true, implies are almost always true, and then look for a true and false situation. True, false. That's the one that you change to false. Okay, let's see this in action on a more difficult question. There we go. Question number 4. Truth table. We have this A or B, and then we have or the complement of C. So this is a more difficult statement. When we are doing truth tables, you only ever want to compare two columns at once, not trying to do complicated things. So what you see is, even if this stuff weren't there, I would create columns for that stuff. Hopefully on the test you do have these blank columns to help you out. But this, I need to figure out what that is, and so I create a column for just that information. This, I would like to visually see what not see is, so I create a column for that. Then I will have two columns and I can compare with the key or, etc. All right, so here we have the or. So we assume true, and a false and false equals false. So we can just go right through here and assume they're all true and get most of this column correct. And now we're looking at A and B specifically, so don't even look at column C for this analysis. We're looking for a situation where there's false and false. If you look at the bottom two rows, we have false and false. Those are the true where we're going to change the assumption. That column is done. Now the not C is probably the easiest thing to do in logic theory, because this is the complement it's outside of, but if there's only two states, true and false, then outside of true is the other one, false. So this is essentially just opposite. That's all not C, or the complement of C is in truth statements. In truth tables is the opposite. So don't look at A or B for this. We're only looking at C. Don't look at this. That's not involved either. We're just looking at the column C and doing the opposite. So it says true, false, true, false, true, false, true, false. We're going to do the opposite. False, true, false, true, false, true, false, true. So where this one was true, this one is false. Where this one is false, this one is true, etc., etc. It's just the opposite of the C column. That one's pretty simple to fill out. Okay. So now that we have these other columns created, we can now look at this symbol, which is the link between these columns, and that again is or, so assume true, and false equals false. So we can go through here and assume it's all true, and then we're looking at these two columns, so don't look at any of this now. Is there a false and false? Right there. That's the only false and false. That's the one that we change. So you're only ever comparing two columns at a time when you're doing the and, or implies. If you're doing the opposite, you're only looking at one column. And false equals false. So, or, assume true, and false equals false, and assume false, and true equals true, implies assume true and false equals false. That gives you a very fast and efficient way of approaching all the truth tables. I hope this makes sense. All right. Number 5. Some cats go to heaven. Shadow is not a cat, therefore Shadow will not go to heaven. Draw a Venn diagram. Okay, so we have some cats go to heaven. So we'll have the heaven circle. Now there might be a bigger circle outside of this. Some cats go to heaven. So, but not all cats go to heaven. So if this is the heaven, the cat circle, some of them have to be in the heaven circle and some of them have to be outside. Okay, so here we see the cats that go to heaven. Here we have the cats that don't go to heaven. And here we have everything else that goes to heaven. So Shadow is not a cat. So Shadow could either be here or, I don't know, is there a universal set? So this gets into questions that I don't usually deal with mathematics. Is there something else besides a heaven? Maybe, maybe not. So this now I would have to start wondering why I put this question on a test. I'm not saying that this is on your test or not, but I'm like, okay, so not a cat. So could be here, could be here. Both of these are options for Shadow is not a cat. So Shadow is not a cat. Therefore Shadow will go to heaven. I think that that's false, and this would be my proof that heaven is not the universal set. If you're going to open up the concept of heaven, you also have to open up the concept of hell, meaning that not everyone goes to heaven. So there must be something else. So I would place this right here as Shadow. Now when you're filling out these Venn diagrams, the circles, the hollow circles, represent a huge amount of things. The solid dots represent an individual. So don't create a shadow circle, because then that would be all things named Shadow or all shadows. That's not what we're trying to represent. It's just a single solid dot, Shadow. So here I have Shadow is not a cat and is not in the heaven circle. So I would say this is invalid. And there's my proof. Okay. My dog did not eat the cat food yesterday. My dog did not eat the cat food today. Therefore, dogs do not eat cat food. And this is a question about inductive or deductive reasoning. So with inductive and deductive, there you want to think in terms of specifics and general. My dog did not eat the cat food yesterday. That's specific. My dog did not eat the cat food today. That's specific. And then dogs do not eat cat food. That's general. It's a general statement. So when we have general and specific, whoa. If we have general information and we're getting to specifics, that's deductive. Whereas if we have specifics and we're implying general, that's inductive. So in this case, we're trying to take specific information and concluding a general fact. Specific information about my dog not eating yesterday or today, the cat food, trying to get to a general, dogs do not eat cat food. The argument is inductive. In making an inductive argument, you have to have a lot of specifics leading to that general before you feel like you have enough information to make that argument valid. This, a dog not eating cat food 2 days in a row, definitely not enough data to show that dogs do not eat cat food, because I've seen dogs eating cat food. So therefore, I have proof. So this would, but this is not, is the argument valid or not? This is just, what type of argument is this? Specifics going to general, that's inductive. General, and it can even be general and a specific, but if anything, general information is trying to get to a specific conclusion, that's deductive. Okay. All cats eat meat. Max is a cat. I wrote this problem and my cat's name is Max. I was wondering if he's in here, I could hold him up to the camera so you could actually meet Max. Therefore, Max eats meat. Okay, is this an example of inductive or deductive? So all cats eat meat is a general fact. Max is a cat is a specific. And we're trying to get that Max eats meat, which is a specific.
Okay.
So we have general and specific trying to imply specific. This is an example of something general along with a specific, that's fine, going to specific. This is deductive. Draw a Venn diagram. Okay, well we have all cats eat meat, so we have to have a meat circle. And all cats eat meat, so the cat circle is inside the meat circle. And Max is a cat, so we need a specific solid point for Max. Since Max is a cat, he's also inside the meat circle. So we are showing that Max is inside the meat circle, therefore our argument is valid. There's no place we can place the Max individual that's not in the meat circle. Therefore, we can conclude in all cases that if Max is a cat and all cats eat meat, Max is inside the meat circle. Max eats meat. All right. Next question. Match each example from the first column to the correct logical fallacy in the second column. Since the 1950s, both the atmospheric carbon dioxide level and obesity levels have increased sharply. Hence, atmospheric carbon dioxide causes obesity. Now this is the correlation implies causation logical fallacy. Just because they're both going in the same direction doesn't mean one's pulling the other. No one has proven the Loch Ness Monster isn't real, so it must be real. This one's probably the hardest one on here. I can give you the answer, but if this were me on the test, I would go through the other multiple choice options first and see if that helps me narrow down the options. So let's go through and see if the other ones make more sense. Ryan Reynolds.
No.
Say again?
I said number 2 is a no. It has to be.
Ryan Reynolds.
Number 3.
Ryan Reynolds owns Mint Mobile, so it must be good. So this is an appeal to authority. Ryan Reynolds is an authority, so he must be true. We can either go to Disneyland or the dentist. You lied to me about cleaning your room, so we must go to the dentist. That is a false dilemma. And either or is in general a false dilemma. Why can't we do both? You grounded me for my phone. Apparently you want me to lose all my friends and ruin my life. So if you take something and make it larger and worse and worse and worse, it's like creating a straw man, meaning I cannot think of the name. The Wizard of
Dorothy?
Oz. Yes, the Wizard of Oz. He's a straw. It's not. They don't call him Straw Man. What's his name? Anyway,
Oh gosh, he does have a name, and we should give him a name. That's right, right?
Scarecrow. So you create a Scarecrow, which is worse than it actually is, because the Scarecrow isn't doing anything, but it seems worse than it is, and it scares the crows away. So that's the straw man fallacy, leaving us with no one has proven the Loch Ness Monster is real, so it must be real. That's an appeal to ignorance. Just because they're ignorant about that it doesn't, that it hasn't been proven real, doesn't mean that it's real. And there are some others. You can go back to the discussion. That's where they were first discussed in the course to look at other examples. But those are the ones matching. Okay. We get to Module 8. Module 8 is about encryption. First off, we have modular arithmetic. Evaluate the following expressions. So 560 mod 31. What we need to do is divide 31 into 560. We will get a whole number and we will get a remainder, and the remainder is the answer.
Oh, that's cool.
The easiest way to do that is with our calculator. It'll turn on, there we go. 560 divided by 31 is a mess. The 18 is the whole number. The remainder is what we need to figure out. So if we subtract the 18, that's the decimal. If we multiply by the 31 that we divided by to start with, we get the remainder. Now, does that actually work? If we went just 2. This is 2.
Wow.
So if we went through the process, 31 goes into 56 one time, 1 times 31, and subtract, that would be 25. Bring the 0 down. 31 goes into 250 8 times. 8 times 31, 8 times 3 is 24. And we subtract 2. Remainder 2. The divide, subtract, multiply steps are the way that you can get your calculator to have you not have to do the long division. So again, 560, divide by 31, subtract the whole number, and multiply by 31 gives you the remainder. Divide, subtract, multiply. Now this next question might be too big for your calculator. We can take a look. What is 305 to the 5th power? Oh, it's big. If we tried to divide by 7, it's too big to subtract the whole number part from. So this problem is on there so that you can use the other formula, and it's in here somewhere. I wonder if I can quickly drag it over. Let's see. We're just going to pop up. There we go. So these are the formulas that you get on the test. And here we have the modular exponentiation rule. We can apply this rule to be able to do the problem at hand. But you have this rule. Basically, oh, that's nice. Not what I'm looking for, though. Basically, what we can do is we can take the 305 mod 7 as if it were its own problem. On this, we would do our divide, subtract, multiply. 305, divide by 7. Subtract the whole number part. And multiply by 7. 4. Nice. So we can replace the 305 with its smaller, decreased simplified form 4. But nothing else changes. So if this number has an exponent, it's a different form of this modular arithmetic. If that first number, the base, is larger than the modular number, you can decrease that 305 by doing mod 7, which we got 4, and then replace that number with its equivalent modular number. Now that we've done that, we still need to work out what's 4 to the 5th. Okay, now we do the divide by 7, subtract, and multiply by 7, and get 2. Now the numbers are small enough on our calculator. That's also 2. That's just random. The answers aren't always 2. But that's how we would do this problem. As we make that 305 smaller by doing it mod 7. And then we have numbers that are small enough for our calculator to handle. You might need to do this type of question or the exponential rule on the test. Now you might have also had homework where you needed to do an online tool to be able to work them out. None of the questions you have on your test will require you to do an online tool. They're all small enough numbers, but you will likely need to use this modular exponentiation rule like we did on this problem. All right, number 10. Use the substitution mapping below to answer the following questions. Encrypt the statement Gauss 8 pi. So it's important to know that the nice numbers, the alphabet on top, going down, this is the encryption. Going backwards, this is the decryption. Most people get the encryption part right, but some people decrypt the message, but what they actually do is re-encrypt it because they go the wrong direction. So make sure you're going in the correct direction. So G, V, A, N, U, P, S, T, S, T. A was an N. T, E. So G-A-U-S-S, A-T-E. This is Z. P is a B. I is a Y. Gauss 8 pi. We have encrypted the statement with this substitution mapping. And encryption goes from top to bottom. So you just find the letter like P and go down, and that's how we replace P with B. This is a simple one. The decryption, T, you look for the decryption. This is definitely ugly. We go to the ugly stuff, that's the bottom row, and then we go up. So this T, we look for a T, there it is, and go up. That first T decrypts to an S. R, oops, R goes to a C. G goes to an A. S goes to O, another S, another O, and A goes to L. Decryption. You know you've done the decryption right when you actually get English out of it. School.
What's the only part of the decryption? I missed it. I'm sorry. I don't know what you're talking about.
So we have a mess statement, TRGSSA, and we're trying to decrypt it. So we go to the messy part of the substitution cipher to find these letters, like G. We locate G,
Yeah, okay.
and then decrypt it to an H.
Okay, I get it. I was just confused on why it was called the messy part and whatever.
Yeah, yeah, okay. Number 11, decrypt the word if it was encrypted using an alphabetic Caesar shift cipher with shift 13, i.e. mapping A to N. So for this one, below A, we place N, and then do the alphabet. When we get to Z, we start over at the alphabet. When we get to the end of it, the next letter should be the one you started with. Perfect. So now the clean stuff is on top, the messy stuff is on bottom. We're decrypting. This is the messy stuff. We go to the bottom. P, C, B, O, Y, L, another L. I'm guessing this spells college. Let's see, R is an E, T is a G, and R again is an E. College. Okay. Number 12 is coming up. I'll find it. It's over here. There it is, number 12. Decrypt the message. Oh, it's a long message. If it was encrypted using a tabular transposition cipher with encryption keyword quart. Okay, so quart, 5 letters. I start by writing the keyword. And what that does is it gives us the number of columns that this table will require. Next up, I count how many letters are in the message. 1, 2, 3, 6, 9, 12, 15, 18, 21, 24, 25. There's a total of 25 letters. There are 25 letters, and this table is 5 across, so it has to be 5 down. We now have a table that's the correct width because of the keyword quart and the correct height because of giving us 25 letters. Now the keyword is an interesting one because we have to think in terms of the alphabet. What letter in quart is the first in the alphabet? And it's the A. So we're going to fill out this table going down with 5 letters. So the first 5 letters, there they are, STAVH, are going to be in the A column. All right, the next 1, 2, 3, 4, 5. The next are MRTLA. We have to figure out what column's next. So we look at the word quart and see what's the second letter in that word in the alphabetical order. And it's Q. So we put the MRTLA in the Q column. Next 5 letters, 1, 2, 3, 4, 5. EITEA. What's the next letter in the alphabet? QRR. Then ST, and then U. We can finish this ordering if you'd like. So the first group is going to go in the A column, second group, third group, fourth group, fifth group, etc. So third group in the R column, this is EITEA. The next group, the fourth, that goes in the T column, CSIM. Oops, that's not an M. Oh my goodness. There we go. M-A. And the last column goes in the last alphabetical letter. The fifth is the U column. So Y-E-H-O-T. Now, place these letters read from left to right.
U-M-R-L-T-H. Y-E-H-L-O-T.
And then see if you can go through and see where the letters, where the words are. Mute you again. There we go. So we have my secret is that I love math. The AA are filler letters. They're not part of the message. And this would be how you use a tabular transcription cipher with keyword to decrypt a message. You might also review how do you use the keyword to encrypt the message as well. Okay, nice. Number 13. You are doing a Diffie-Hellman-Merkle key exchange with Kira using generator 2 and prime 29. You pick the secret number 10. What is the value you will send to Kira? So the process of the Diffie-Hellman-Merkle key exchange is you choose the generator and prime that you and Kira are going to work with. You pick your secret number. You use the generator and prime to get an exchange value that you send to Kira. She does the same stuff with her secret number to get an exchange value. You give it back to you. And then you guys use the generator and prime one more time with the exchange values and end up with the same encryption key. You then use that encryption key with some encryption method, and you guys can have your own code, essentially. Here we have the one-way functions. They're basically all equivalent looking. It's not letting me highlight or anything. Let's highlight them. Maybe. There we go. The GN mod P, that's the Diffie-Hellman-Merkle version of the one-way function. The ME mod N and the SD mod N, those are the RSC encryption method questions. So G to the N mod P, that's what we have to work with. So let's write that down. That formula is given, you just have to know which one. Which version you need. All right. So the generator G and the prime P are given. The N is your secret code, secret number 10. So we would do 2 to the 10 mod 29. This would give us the exchange value that we'd send to Kira. Let's see what it looks like. I think 2 to the 10 is small enough that we don't need the exponential rule. Divide, subtract, multiply. The number is 9. That's the value we send to Kira. She then takes that value and combines it with her own secret number and comes up with the key you will use. That's it. Now, if we were to do the other side, Kira sends us the exchange value. We still need to mix it with our secret code. So the 10 remains the same on the first half and the second half of this process. And the prime number 29 remains the same. So the 2 is what changes. So number 14 is the second half of this. We're doing the Diffie-Hellman-Merkle key exchange with Christine using generator G, and prime P. Your secret number, that's N. Christine sends you the value 5. Now in the G to the N mod P, we have the prime number. We have our secret number. But if we use G as 3, we will get the exchange value to send to Christine. But if she's sending us the exchange value already, then we've already done the first half. So in this problem, the G is what she sends you. So we end up not using the original generator G at all. That's for the first half of the process. So we would get 5 to the 12 mod 17, and this should be small enough for us to go through. Oops. Ooh, that's a big number, but it's small enough when we divide by 17. I can see the whole number part. Subtract the 1, 4, 3, 6, 1, 2, 1, 3. And then multiply by 17. Rounding error here, but we can see that number trying really hard to be 4. So, now you might ask, that number was big enough. Can we use the exponential rule? Comparing the exponent now with the mod number, it's only if the base of the exponent, it's only if that number is larger than the mod number that we can make that number smaller with the exponent rule. We cannot apply the exponent rule because that base is already smaller than the mod number. So we just had to use our calculator. It gave us a slight rounding error, but we can interpret that as a rounding error and know the answer. Sweet. Next up, Alice has shared that her RSA public key is n equals 33, e equals 7. Use this to encrypt the number 2. Okay. We have 2 formulas here. The E is for the encryption, E. The D is for the decryption. The M is your original message, and the S is the secret code. That can help you remember which one to use. So we have encrypt, decrypt. We're going to use the encryption, ME mod N, for our first one. So this one's going to be M to the E. Oops. Mod N. Whereas this is going to be S to the D mod N, because this is the decryption. Okay, so we need the message. We're encrypting the number 2, so the message is the number 2. E is given as 7, and mod N is given as 33. That's just calculator work now. Two is smaller than 33, so we cannot use the exponent rule to make the number smaller. So we just go straight to 2 to the 7, 128, divide by 33, subtract the whole number, and multiply by 33, and we're looking at the remainder, which is 29. That would be the coded or the encrypted number. Mike has just shared his RSA public key is n equals 33 and e equals 7. His private key is D, the decryption key. No one else knows that but him. hopefully. He was sent the encrypted number 16 and he wants to decrypt that number. So the secret is this 16. We don't know what it represents. D is the decryption key. And the N is still the same public key information. Once again, 16 is smaller than 33, so we cannot use the exponent rule to make the numbers nicer. So we just go straight through 16 to the third. Divide by 33, subtract the whole number, and multiply by 33. And we've decrypted the code of 16, and we got, there we go, 4. That is the application of the RSA encryption and decryption protocol. That also completes this review. Hopefully it has helped to have someone use English to explain it. That's not necessarily, actually you probably heard the same English as I'm explaining it on the videos as well, since I made the videos for the class, but I hope this helps. And at this point in time, I'm going to stop the recording and then take any private questions if you have any. Maybe.